So to the grad students, next Friday, what I would like to do is, during class next week, I'm going to circulate a little piece of paper to schedule a time to meet on next Friday with the grad students one-on-one to discuss the current progress in your report. All right, has nothing to do with grades. If you don't want, don't come. But I think it's going to be a lot better for you to come sit with me all of 5-10 minutes, right? And I'll give you pointers of how I think you're doing, right? So it's just trying to help. So during next week I'll circulate that. But just think, you should, by next Friday you should have something that looks fairly fleshed out. For everybody, final, right? You wanted to ask me about the final? Okay. So have you checked on beer tracks? So we have a date and a room for the final, right? Okay. So we're good with that. So we are going. We're doing so super well since now we have seminars and we are having the exams in the evenings. That has opened up time. What I want to do today is to wrap up our calculations of how to dimension a fillet weld, right, which we had discussed. I'll start with a very quick recap. And because of your awesome TA, Mitch, we prepared something that is a little bit beyond that. If you remember, we said we'll discuss only symmetric loads. Okay. I think we can discuss a little bit of how to deal with asymmetric loads. We're talking serious stuff. So, okay, do you remember this thing we discussed, right? Like the fillet welds can be longitudinal or transverse. Do they behave the same? If the same fillet weld with the same electrode and the same procedure, do I have the same strength in this transverse weld that in this longitudinal weld? No. Right? Which is stronger? Which is stronger? Transverse, right? But you had this insight that I thought it was fantastic. The transverse is less ductile, right? Because you have like a smaller characteristic length to the form. This one could deform over a long length. But the trade-off of being more ductile is that it's less strong, right? So transverse welds are stronger, but longitudinal welds are more ductile. Same material, so this is not a material property, but it's a system property. Super interesting, right? This matters because we have a couple Mekis here, right? And you believe, hey, steel has this strength and this toughness. Well, no. No, right? In a standardized test, you're going to get something, but when you put it in practice, things change. Then we said something interesting. We said, if we have a combination of welds that are, say, longitudinal and transverse, right? Do all welds develop its full strength? Right? Somebody said no, right? Why? Why no? Why not? If I were to have a weldment that has combination of longitudinal and transverse, why can't I use the strength of the longitudinal and the strength of the transverse and be happy? Why doesn't it work? Because it doesn't. Why was that? Right, exactly. By the time this fails, this hasn't developed the full strength, right? So, I mean, yes, this can eventually develop its full strength, but why would I care this developing the full strength if I already missed a whole seam, right? Things are going pretty wrong by then, right? So this is cool. This is in the Canadian code. The way they teach you how to calculate welds in the US, they don't account for that. Interesting, right? And I need to talk with my colleagues and find out more to see. I'm not familiar enough with the US codes to see why they don't, right? But that we do in Canada, and you will do it in this class, right? We are so much more advanced. So, and then we go through this, and here's where we stopped last class. And this is the formula of life. And this is a formula that, although it looks somewhat involved, is just plug and plug, just multiplying simple algebraic things. And incorporates lots of things. So let's go over this again. Now, this is what I would like to do. I would like to go over this formula in proper detail with you, explain you where to get the values for this formula, discuss it briefly. I'll go and wave my hands over one example on this, right? And then Mitch in the seminar, he will go over the example step by step. Those examples are already uploaded because they are from previous exams. And then what I want to do is discuss what happens when we have a weld that is not a symmetric load, that has bending or twisting. And that is super cool. And that is the first thing we would do. All right, the formula of life. First of all, I have no idea why they chose this notation, right? But probably in civil engineering, the notation makes sense. V is force, right? Resistance per unit length is newtons per meter, right? Or kilonewtons per meter, or kilonewtons per millimeter, whatever it is. Okay, so here we have this force. And it says that the force, okay, let's wind back. The central concept to this calculation of welds is assuming the weld is just a line, right? We assume that the weld is just a line, and this line has a force per unit length. Of course, a weld is not a line. A weld has a size, right? We're actually going to be calculating the size of that weld. But overall, the size of a weld, the width of a weld, is very small compared with the size of the component. So, I don't know who, maybe Dr. Omer Blodgett at Lincoln, I'm sure many of them also came up with this at the same time. They said, the weld is so narrow, we're going to consider it as a line. And this line has one property that matters, is how much force it can take per unit length. That's the one property of the line, and that's all we care about. And here's the force it can take per unit length. And the CISC in Canada, our code say this is the way to calculate how much force your weld can take per unit length. Here you have a 0.67 that nobody tells you where it comes from, but it relates to many statistics and also relates to the relationship between tensile forces and shear, right? At the throat, you fail by shear. And, but we're going to be using properties of tensile test. Okay, so that's this 0.67. This phi here, for the Americans, this is a safety factor. For us, is a limit state. And unfortunately, despite all the knowledge of welding I crammed in my head, I still cannot tell you what the real difference is between limit state and safety factor. Civil engineers would go crazy about how different it is. In the end, the number is the same. So what I can tell you is this is based on lots of statistics in which they welded with all types of electrodes, all plates, much of that done in this university. But for you, in your exam and in your professional life, you put a 0.67 there, that is much more or less what the Americans do. So here you have this 0.67 here, because it is AW. AW is the throat of the weld, right? The throat, not the leg. This is the throat of your weld, because we say it's going to fail on the throat. Here we have the area of the throat of the weld. And this is in meters, right? Meters. XU. XQ, and again, how did they come up with this notation? XU is the nominal UTS of the weld metal. Civil engineers. My daughter wants to do civil engineering, so I should be kind to them, right? But so XU is the UTS of the weld metal. Here's the first interesting thing. We're talking about failure of our weldment as failure when they reach yield. But we're using the UTS of the filler metal, right? It gets tricky. So sorry, I said it wrong. We use, for the properties of the base plate, the yield, right? When we say matching electrode, it's an electrode that has same strength as the plate. But the plates are cataloged by yield strength, but the electrodes by UTS. You know the difference between UTS and yield? Anybody? It's okay, but this is the time. All right. Yield and UTS are not the same, right? When it breaks, right? And a yield is when it starts to deform. And UTS tends to be, depend on the material, quite a bit higher, right? Okay. Now, then we have this thing here. This part here is something that typically is not in the way you calculate weld lengths in the US. And I need to learn more, but I don't see this in the American literature. What here it says 1 plus 0.5 sine of something. This theta is this theta here, okay? So if the weld is longitudinal, what is theta? 0, right? Okay. If theta is 0, sine of 0, how much is that? 0, right? So this 0.5 doesn't count for anything because it's 0 to the 1.5. Then I have a 1. So this is kind of some sort of a correction factor that gives you credit for transverse welds. Americans don't tend to take that credit, but we do, because that will result in thinner welds, right? So this is a cool thing. So this 1 plus 0.5 sine of something is giving you credit, a 50% credit for a transverse weld, right? What this says is that this value here is 50% more than this value here, all right? It's pretty cool. Now, this MW says, all right, I'm happy you're taking that credit, but remember, by the time you break the most transverse weld, the longitudinal welds are still not fully done. So now I need to knock it down, right? So this MW here has this expression here. This is theta 1 and theta 2. Theta 1 is the segment we're considering. For example, that's theta 1, okay? What is theta 2? Theta 2 is which segment is closest to 90 degrees, right? So if you have a segment at 90 degrees, 90 over 600 is 0.15 plus 0.85. This would be a 1. So MW would be 0.85 plus this other factor. Now, imagine my weld, in my set of weldments, one of the welds is not 90 degrees. For example, look at this, kind of right here. I don't like it. So let's say all right, look at these two weldments, which are somewhat of an extreme case. Do you like my weaving in my weld? There we go. Wow. You see, this is called productivity. If we could weld like this in Alberta, we'll all be safe. No, don't weld like this. Okay. There you go. So I'm pulling in these plates. Huh? Longitudinal, right? This is very ductile. Diagonal. So this is going to be less ductile. And this here is transverse, least ductile. All right. Question to you. Okay, fine. Will this weld here develop full strength? Why not?
The transverse, yeah.
Where is it transverse?
The transverse portion of it?
This is a diagonal, right? This has a phi here associated with it. What do you mean by transverse portion?
The ones with the higher theta would probably.
Okay, which is the one with the highest theta? Is this, right? So I ask again, will this develop full strength? How about this? No, right? Good, okay. Will this one develop full strength? No. Why? Because of this guy here, right? Now, that's what this formula is taking into account, right? That in this case, although these two welds look much the same, I'll get full credit for this weld here, but not full credit for the weld here, because this will break first, all right? That's a very smart code. And I don't know how they came up with this formula, right? But we can account for like a pretty complex factor, right? So we have two things. One here is I'm getting credit for the transverse, how transverse a weld is. And here is I'm getting a knockdown because I will not get fully developed strength. Okay, this is super cool. Okay, and here are the formulas to use. One is 1 plus sine. You put it, there's no mystery in that. Huh? And this other one, you put these 0.5s in here, and you get it. So, for example, in this case here, this weld is theta 1 and theta 2 would be the same, right? Because this is theta 2. So that's why the MW is 1. But in this other case, we have let's say this is 30 degrees, right? 30 degrees here, theta 1, and 30 degrees here. But in this other case, I would put 30 degrees for this weld here, but here we have 90. So it's a knockdown. I think it's pretty cool. Anyway, so if you use overmatching electrodes, you have a new trick that can happen. So maybe now the throat is not going to break. I mean, if I use an electrode strong enough, it's not going to break at the throat. It's going to pull from the leg. So there is an alternative calculation that you do when you use overmatching electrodes. That is this one here that says, my weld as a line has a strength given by this 0.67, just as before, my limit state, 0.67, same as before. Now it says AM, and I don't think I put it here, but AM is now the leg. It's the size of the leg, not the throat, right? Because now we'll be breaking at the leg. Like, so, it sounds kind of odd talking in a class about breaking throats and breaking legs. It sounds like Gangster 101 or something. So you can break the toes too. Like, you can break so many things in welding. So AM is because it would break at the leg. And here you have is FU, right? And nobody get too smart about the FU. Is the civil engineers. So it's the nominal UTS of the base metal. Now it's funny. For example, if I have a 7018 electrode, what is the nominal UTS of 7018? 70 KSI, right? Easy peasy. But the steel, like 430W or something, has 430 megapascals yield. Okay, what is the UTS? You don't put 430 or whatever equivalent would be there. You have to go to a table. All right? So I want to show you those tables, which will be in your formula sheet in the exam, and are tables from the code. And this is the way engineers work with these things. So you design the welds for UTS. Okay, first, here is the matching electrode and with the UTS of the plate. So when we say matching, we talk about matching UTS. So Canadian codes are in metric, which is a big travesty because you write the code in metric, but you do everything in imperial. Fine, that's the way it is. So the code says electrode 430, right? In metrics, a 6010 is actually a 4310, right? So this would be 430 UTS of the electrode, and they match. Look at what plate, 200 or 300, right? You say, what part of matching am I not getting, right? 200, 260 with 430 or 300 with 430. Shouldn't be like more like 400? Why the matching is not matching here? Anybody will tell me? Why I'm not matching a 430 electrode with a 430 plate?
The voltage should always be stronger than base metal. You choose electric.
Yes, but that's not matching. When you say matching, although it's true that when you test it, you want to break it at the plate, not at the weld, you still call it matching, right? Well, what happens is that a 430 megapascal electrode has a UTS of 430 megapascals. But a plate of 430 megapascals of UTS is actually 300 in yield, right? That's a reason why this matching looks odd. And like many things in welding, if you look back, you can think of smarter ways of doing it, but fine. Like this is the way it is today. So 7018 or something is 490 UTS. Would be good for, it would be considered matching for all these grades of plate, right? And you say, well, am I matching this or am I matching this, right? Kind of. It's a little bit of this wiggle room in welding. But you get to see a trend, right? Lower strength plates go with lower strength electrodes, and higher strength plates go with higher strength electrodes. That's how the trend works. And we live around here. Yeah, we sell them, yes?
Okay, so I see where there's the MPA, but I'm struggling to see where it shows the grades.
Oh, the grade is 300 MPa. Right? 260. So these are this is the standard for naming the steel, and this is the grade within this standard. So you'd have I'm going to show you like you would call it like a 430W steel, right? Sorry, 430 300W steel, right? 300W, 260W, something like that. Right? These are the standardized grades. We good or more or less? Okay. So there you go, the 300W. Not good, right? Okay, let's start again, because what matters is that you learn it. I don't care about like being comedian. So where did I lose you? I asked you because you had the courage to say it.
I started to think. I think it's because I'm not used to people saying things like X70. And now
Okay, so people would say X70, and people would say 1040, and people would say P1. Crazy stuff. Okay, so this is a story. A steel is a steel, right? Now, to do commercial transactions and to do engineering, people came up with standards. So we would have a proper name, like when you want a stronger steel, right? It might need to be weldable or not. So the people who care would say, well, for these applications, you would have asked me, and they would say, oh, carbon steel, we're going to call it P1. And you go to SAE or AISI, and they would call it, I don't know, 1020 or 1040. Right? And then you go to other codes. For example, in this CSA, they call it G40.21, right? And if you go to ASTM, the same steel can have very many different names. The X70, that's an API standard, right? And it means a bunch of things, right? But an X70, I don't remember if it is UTS or.
So 70 and 70 KSI yield. It'd be grade 4 E3, we call it typically. We call it grade 4 E3.
Okay.
They'll weld X70 with 80 KSI electrodes and call it matching, but it's not technically matching. But that's more like a unique quality of the pipeline codes. So in this case, for a similar steel, which would be the 480W, they're suggesting 90 KSI. That's actually matching or probably a little bit exceeding.
Right. So in any case, you say X70, and all those things can be confusing. Right now, we're focusing just on the standards of CSA. But in the end, when you say matching electrode, you look at the UTS of whatever steel you have, so, and the UTS of the electrode should be more or less the same. Does that kind of make sense? Maybe I should start like that. Yeah.
One thing I would say is these grades, and I think it's a little bit of a lie anyway, because this is all minimum. So if you have a X70 steel and you tensile test it, you should not expect that it's actually going to have a yield strength of 70 KSI. It's probably going to be closer to 75, 80, because that's a minimum specified yield strength. And these are minimums as well. So there's always going to be some variation in practice. That doesn't make things easier, but.
No, because if a steel is stronger, probably has more alloying elements, right? If it has more alloying elements, probably it's more hardenable. And if it is more hardenable, probably when you weld it, you might end up with hydrogen cracking or something like that. So it makes sense to know. Most of these problems in welding come down to these things we would know. But we didn't think much about. All right, so this is the way we pick for what plate, what matching electrode we would have. And you will have this in your formula sheet. Here, you have the relationship between the yield strength, right, and the UTS. So look, this is what Mitch said. Yield strength minimum, right? A 300W should be 300 typically, right? A 350 should be 350, right? And but could be more. That's what the standard says. This is the yield strength. But now we have the tensile strength here. Look, the one that the 300 that should be 300 actually is 440. And the 300, right, which is 440, is a pretty good match for this 430 here. Right? Let's see, 350 would be 450 to 650. Right, 450 to 650, like this is somewhere like in there. That's the way to go. Remember that this thing of matching is not an exact science because it's all based on standards. But when you do a procedure, you can have higher or lower heat input. If you have two heat inputs and one is higher than the other, what do you think the effect on strength is going to be of a high heat input? Lower, right? Because high heat input means lower cooling, which means fewer of the hard phases and more of the soft phases. So they write all this. But as you see, they never are saying, if you do it with this heat input, right? That is in their standard. But nobody says, if you're welding with a different heat input, you should change. And in this limit state that we discussed, people weld with many heat inputs and in many conditions, such that in the end, when you start changing the heat input, it's already taken into account into the limit state factor, and you're fine. So you're going to see in previous exams, I asked, okay, I qualify my weld and I design my fillet. If I have lower heat input now, my weld is going to be stronger. Should I redo my calculations? The answer is no. You do the calculations according to all the standardized procedure, these standardized steps, in which you don't get credit or you don't get knocked down for the different strength that comes with different procedures. Right? That's the same with configuration you have here. Right? It's very not the same. Well, the thick plate, that thin plate, and fillet. It's all in the statistics they did. All right? Very, very, very interesting. And much of these things we're talking about here is things that would be so difficult for us to think if we sat down and thought in a scientific way, because there are too many things that can confound us. They just went and did it and say, you do it this way, and buildings don't fall down. And of course, the weld is quite scientific, but there are many things they gloss over intentionally. Here's another thing that is part of the standard. You do your calculation, and you end up, you needed a fillet of 1 millimeter. Should you do a fillet of 1 millimeter? And the answer is no, because 1 millimeter is too small. Remember when we talked about the bond number and why we cannot make an enormous weld? Because it's going to spill and run like liquid, right? That's the reason we cannot make huge welds. Conversely, we cannot make too tiny welds, because if the weld is too tiny, the bond number means the capillary is too tight, and the weld would not wet. So it would be very difficult for the welder. Okay, there's another reason why people don't want to have too small welds. Actually, I thought of that, but then when I looked into practical tips that you can find on the internet, they mention it. Anybody would want to tell me what problem would I have with too small of a weld? No, actually, a small weld would give me less distortion than a big weld. Imagine I could make a 1 millimeter weld. Why shouldn't I do it? Right. Yes, and you would have cracking, because in the end, the standard tries to prevent you from being a fool. But there's a limit. If they don't say minimum weld, you can still break it, right? So if you have too small of a weld, the cooling rate is too high, and you might end up with cracking, right? Hydrogen cracking to a hard microstructure. So for this reason, they say, okay, don't do single passes that are too small. And also, if you have a big plate, you can still make a 3 millimeter weld. That's okay. But if I have a plate that is too big, right, there is some kind of common sense in which the thing should be able to bear its own weight, their own weight. And these numbers here, not this one, because this is for like a single pass, but these ones are based on common sense. You don't derive these minimum fillet size from equations, but from experience, saying you're not going to weld this big plate with a 3 millimeter weld. Kind of wouldn't hold its own weight, right? Those type of problems. Right. Here. And they also tell you what the biggest weld should be. And I'm going to make a schematic here because this is interesting. Why would they tell me a maximum size of the weld? Why can't I do any weld I want? So we're welding these plates here. And says, don't make a fillet any smaller than this. Fine, I'm okay. Right? Okay. But it says that the fillet should be, when this thickness is more than 6 millimeters, it says it should be T minus 2. Leave 2 millimeters here. Why can't I go all the way up? Could be, right? But what there it says is T can be huge. So this can be a multi-pass weld. So I can still make small passes, right? I can make small passes, but whatever I do, I cannot reach closer than 2 millimeters.
A few of you who did MIG welding with me, we talked about this.
So welders cannot hide.
Right. So because if you don't do this, you can say this. But this is an honest person thing, and that's okay. But you can also do this, right? And to the inspector, it would look the same, but you have no weld there. And you did it pretty quickly, right? Remember when we discussed, like, no welds are good for, nothing welds are good for nothing that I mentioned? This is a nothing weld, right? If I were to weld here, to do this weld here, there is no connection, right? I would have this tiny throat instead of the huge throat I meant to have. So the reason they said leave 2 millimeters is so you don't cheat. Now, people are doing mechanized welding, automated welding. Now you don't need to do this. In many cases, you don't need to do it, but it's still in the code. I think it's a pretty interesting thing, isn't it? I think it's a pretty interesting thing. Don't cheat, the anti-cheat code. By the way, I modified the slides and I upload them again today. So if you're using the old set of slides, doesn't have these, the new set of slides has it. Something else I found, if you look at our old problems, right, our old examples, of course you have to round up the numbers. And I will round them up to like 5.5 millimeters. Well, I just learned you don't do that. These are standard fillet sizes. 3, 5, 6, 8, 10, 12. Not 9, not 11, not 13. Right? I mean, imperial would be 1/8, 3/16, right? You go every 16 up. That's the way inspectors are used to see it. Now there's an interesting thing. The metric, if you get an imperial design and you pass 3/16 to 5 millimeters, you're on the safe side. Same with a quarter, 5/16, 3/8. But half an inch, how much is half an inch in millimeters? 12.7. But we do 12. Not 13, and 13s are uncommon. So I don't know exactly how you handle these type of things. Same with 1/8. 1/8 is 3.35 or something like that, right? Not 3. But this is the way we convert them. In practice, you seldom make passes less than 5 millimeters. You could do 3, but you seldom make less than 5. And in practice, you seldom make welds bigger than 8 millimeters. Right? Those are handy numbers. All right? So I will wave my hands over this example, which you're going to take one of these 3, right? Okay. In your notes are 3 examples, some of which, like I round up to 5.5 millimeters. You don't do that, because now you know that they're standardized fillet sizes. We're better than previous class. All right. If we have this force here pulling from this plate that is welded onto this other plate, right? And this is 300W steel plates, right? And because we went to this table, we would know it's 440 megapascals. How big a fillet do I need to make for this? And the only question you have to ask is something we discussed before, is we design for the load. Of course, according to the code, there will be a minimum fillet size and all that. So we are going to see first, and the other thing we know is that it's better to have a thin, long fillet than one big, massive fillet. So I could do a thin, long fillet all around, or like one massive fillet right here. But if you remember, a fillet that is twice as thick takes would be about half as short, but takes twice the amount of material, right? So we would have, when we do thick fillets, we end up having a strength per unit length that is lower than what we do. When we do thick fillets, we end up having a lower strength per pound, strength per unit mass, than if we do a thin fillet. So, okay, let's go for a long fillet all around. And this is the way we calculate it. I'm waving my hands. Mechi's going to do it right, and in preparation for the final, you should do it. This is fairly simple. Here's the formula. That is going to be your formula sheet. This is all you need to know. Now we're going to divide this weldment into all these parts, right? We have three types of welds: longitudinal, like diagonal, and transverse. Okay. So the way we do is we calculate not VR, right? Not the force per unit length, but we're going to pass the leg size, the throat size down here. We're going to calculate VR over AW. This is the reason. If I pass this down here, I know 0.67, this is 0.67. I know this because it comes from my electrode. I know this because it comes in the design, what the phi is going to be. And I know this because it's given by the design. So I do not know my throat size. I know everything else. So I'm going to pass this down, calculate VR, the force per unit length and unit throat for each segment. And this is what I did here. We have segment A, B, C. And here we have the phi W, that's 0.67 always. XU, right? That is the UTS of the plate. Sorry, the UTS of the UTS of the electrode that matches the plate, right? We said here, use matching electrode. So use matching electrode, you go to this table, right? That is the table we discussed, and you say, okay, the matching electrode, let's do it. 300 W plate. 300 W plate, we should use, this is for hollow section, right? So, no, not, so we'll do this. 300 plate, we're going to use a 70-something electrode, like 7018. 490 ultimate strength. 490, right? For A, the force goes in this direction. A is longitudinal, B diagonal, C is transverse. MW looks at what is the one that is the most perpendicular. That's theta 2, and this one in this case is 90 degrees. And then theta 1 would be in this case. What is theta 1 for weld A? That would be 0, right? Because it's longitudinal to the load. What is theta 1 for weld C? 90, right? And for B, it's 45 degrees, right? And that's what we have here. And with this, we calculate the MW, this factor. And, we have the length that comes from all this design. So we calculate this. Then we calculate the strength per unit length and unit throat, and we multiply it by the length, right? That would be the second step. We multiply it by the length. So this weld can take so many, did I put it here? Can take 187 newtons per millimeter of length and millimeter of throat. Then I'm going to multiply it by the 100 millimeters of the length of the weld, right? And then I do the same for each of them. So I multiply this strength per unit length and unit area by the length, right? So then I add them all up. I add them all up. And then what do? I know my strength per unit length and unit throat. I multiply by the length, so I would have the strength per unit throat, right? So I have the top load. I divide by my strength per unit throat, and I get my throat. And that's what I do. So divide by the sum of these. This gives us the throat. Throat, we're talking about a fillet that is equal legs. It would be 5 degrees. So the leg, what we specify in the design is the leg, is going to be longer or shorter than the throat, the leg. Longer, right? Because, let's see if this works. If this is my throat, right? Here is the length. Right? That is square root. Right? Square root 2 of the throat. And that's what, or we divide, right? Here. And bingo, there you go, the leg. 3. What fillet size should we use? Hmm?
5.
No, you always round up, right? You never round down, right? So what would it be? Say?
8.
6.
Maximum 6. 6.
Right? So I think in the exam I suggested to do 5.5, but no, you don't do 5.5. Oh, look, I have the steps. And like this, a few more. So how are you feeling about this so far? So overall, the concept is this. I know the load, and I need to calculate how much my weld can take per unit length. And the unit length and unit throat. And we have a formula for that, straight out. And that way we design the throat. And this is formula is very powerful. We're doing simple square fillets, but we can have a crazy fillet that would have a much more complicated way of calculating that this square root of 2 factor there. No problem. We can calculate it with the same formula. We can calculate things in which we have forces that are fillets that are like transverse, longitudinal. Very powerful. Questions or comments? Yeah.
Why do we pick a symmetrical fillet? Why don't we have it be, 3 millimeters on one side?
Okay, excellent. Of course you can. Of course you can. And actually, sometimes you have no choice. Let's see. So I'm going to. So, of course you can. Look at this. About this that is new. There are many cases in which you might want to have a fillet that is like this. I don't know why, but it happens, right? Might be a single pass or might be a multi-pass, right? What is the throat in this case? I'm going to make it bigger so everybody sees it. What is the throat in this fillet that has different legs? This is one leg. Here's another leg, right? Very different. How do I calculate the throat here?
Perpendicular to the...
Thank you. To the what?
To the face.
Thank you. Perpendicular to the face. So the throat is whatever is perpendicular to the face. So then mechanic, it's a game of trigonometry, right? So you could have a fillet. How about if you were to have something like this? No, the legs are the same. But it's not, you don't have a square root of 2 anymore. But the legs are the same. What's the throat in this case? Same. That's the way it is. Perpendicular to the face. So in all the previous exams, we had like a very, very simple throat. But this is just a game of trick. Now, if you know that what the throat comes from, tricky one. What's the throat? What would you say? The throat is here.
From the toe to
The toe to here?
perpendicular.
But that's not perpendicular to the face.
Not the face.
Yeah, this is the throat. No. This is the way you calculate the throat, perpendicular to the face again, in this case. Isn't that interesting? So it always goes perpendicular to the face. So let me show you. I think I have some slides on this. This is uploaded, so you have all these examples all worked out and previous examples. There you go. Perpendicular to the face. The throat. Now, you would argue if it wouldn't be to go from here to there, I think that would be, you'd calculate a smaller throat if you do that, right? They don't. I don't know. We go perpendicular to the face. Here, 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 perpendicular to the face, perpendicular to the face, perpendicular to the face. Here we have for partial PJP, partial penetration welds, how you do the throat. What do you think? We know how to calculate the throat at least, right? And that's the number that goes into the formula, because we assume, these formulas assume that you break at the throat. So you don't go crazy about is it going to break a leg unless we do overmatching? Okay. Different loading conditions. This is new, and I want to share this with you. Imagine we have this kind of C-channel welded to a plate and with a load here. You don't know how to calculate that. Imagine we have this kind of gusset here, and there is an eccentric load. You welded it all around. You don't know how to calculate that. So I'm going to teach you. It's going to be awesome, because we needed to weld some things in the lab that we didn't really know how to. Had we known this, it would have been a lot easier. So what they did, using the concept of force per unit length, right, of weld as a line, they said, depending on the type of forces we have, the type of force we have, what formula we use. If I say tension or compression, you would know what I'm talking about, right? Very easy. If it is a tensile test, you do force on area. right? Very easy. And here you do force. You see, now they're using P for force instead of V, right? But this is from American literature, from the welding handbook. This is force divided the length of the weld, right? For tension or compression, right? So I'm pulling on a bar that is welded all around. I distribute the load by the length of the weld. Let's imagine we have shear, right? Shear, this V is the shear force divided the area. This is kind of, so there are better ways of calculating it, but fine. And they do the same. Shear force divided the length of the weld, right? The length of the weld times the throat would be the same as area in this case. So imagine now you have bending, which is the case here, or the case here. If you have bending, when you did the 60 to 70, did you calculate stress for bending? Okay. This is a formula you know. This is moment over the section modulus, or moment over modulus of inertia times the distance from the neutral axis. Right? It's just a formula, and I'll tell you how to plug things. And the funny thing, you knew this. This is the equivalent for welding, is moment over the section modulus of the weld as a line. And the same for torsion. This J is the polar moment of inertia, and this I is the moment of inertia around one of the axes, the transverse axis. Right? Same thing. So if you remember, we just discussed how you calculate force, the strength of a weld per unit length, right? You know how to calculate that. And now I'm saying how to calculate what the strength, the effort per unit length would be in these very difficult loading conditions. So you know how to calculate how strong your weld is. And saying, well, in cases that are not Mickey Mouse like these ones, this is very easy. You have this, very complex. It's more or less the same. But now you have to go through these formulas. And here we have moment of inertia, or polar moment of inertia. And here it says, okay, so if you have this I-beam here, the moment of inertia is going to be around the x-axis, is going to be given by this formula where D and B, right, are in this schematic. And the moment of inertia around the other axis, because you can have bend on different sides. You get them straight with this formula. This is for polar moment of inertia for torsion in a circular base. And here you have more. Here you have for a weld in the shape of a C. And here you have for welds in the shape of T's, welds in the shape of like all kind of different things. So here's an example. And what I'm going to do here is wave my hands through this example. Is that right? Okay. I'll wave my hands through this example, then you're going to do it right with Mitch. So I'll wave my hands. We'll take a few minutes. I think we might finish the class about 5 minutes early, but it's going to be good because I can tell that you guys like are totally spent. The semester is ending, the day is ending, and I'm bringing like a slide full of minutes to you. I'm aware. But this makes you powerful. None of this you need to know, you need to memorize. Okay, so here we have the example that is this case, right? You have this gusset, you have a force that is eccentric, right? And this is from the AWS welding handbook and has it both in metric and in imperial. And this is an example that was done like in the 60s by Omer Blodgett, and forever people keep rehashing the same example. So how do you decide the weld size when the weld is all around, but the force is coming on this side. This is not something you knew how to do. So this is the way you go. You calculate the force that the weld needs per unit length for each of the stresses it has. For example, if I put this force here, this is going to generate some twisting, right? And if it generates some twisting, there is going to be some horizontal force in here. Are you all with me on that? Or not? Oh, the crickets are deafening. Okay, let's do it. I care that you get it. So, in this example, this is welded, and you put a force here. So this force here is going to have the effect of torquing this thing here, right? If I'm torquing it here, this is essentially putting forces here, right, on my weld. Right? Also, this is putting some amount of force down. Let's use another color for the markers. You follow me on that? Okay. So, all right. Okay, so this is what the guys did. They said, let's calculate the horizontal force. This blue one from this twisting in here, right? Let's calculate that force. And that force is the torque, right? The torque is, they didn't write it all too well, but here you go. Torque is this 18,000 pounds times 10 inches, right? That's the torque. That's the torque. And the formula for strength per unit length, here we have it, says is we have this distortion is torque times distance from the neutral axis to the extreme fiber, and divided the polar moment of inertia. So we have torque, the distance to the neutral axis is, in this case, for the horizontal force, is neutral axis is d/2, right? This is d/2, and the polar moment of inertia. And where does the polar moment of inertia come from? The polar moment of inertia comes from this formula we have here, this JW here. That is this big chunk of formula we have here, right? And this is what they calculated here, right? So I'm waving my hands here. Mitch is going to do this, right? But you have this force that we have a formula to calculate. We only needed to know the polar moment of inertia. We have another formula to calculate. And with that, we can calculate an horizontal force, right? And it says this is going to be this force per unit length, 410 newtons per millimeter. Fine. We also have a vertical force for the same reason, right? We have twisting, and the biggest distance from the neutral axis is this distance that goes between here, here's where neutral axis is, to here, right? And that is tabulated. So this is this CYR. So we have the torque, which we already calculated. This distance to the neutral axis is given here. You see CYR? This is bigger than this. in this case. CYR, I have a formula, plug and chug, and I get this distance. So we have torque, we have the distance to the farthermost fiber, and divide by the polar moment of inertia, which we had a formula we already calculated. And this says that our vertical force is going to be this 306 newtons per millimeter. Are you following so far? So we have an horizontal force right? This is our center of gravity. So we have an horizontal force that is given by the torque and this distance, right? Anywhere in here. And then we have a vertical force that was given by here, that is the distance to a vertical axis, here and here. So you get to see these points here so far, right? They have the biggest load, the peak load. All right. And in addition to either of those two, we have the force from the shear. Force from the shear, right? And the force for the shear, where we have, we decided it's force divided the whole length of the weld, and that is applied evenly all over the place. Okay? Okay. Now we're going to do the resultant of all these three components. So, of course, it's going to be like the sum. Let's pick on this one. We have an horizontal force, right? We have a vertical force, and also we have a force that came from shear, right? To put this in red. So, and I need to do this better. So look at this. Shear plus vertical, compound with this other one that is orthogonal. Shear, these two together, square plus this other square, this is the resultant force. This is what you didn't know how to do. Now you know. And now what is the next step? Oh, here, the things you know. Now you know what force per unit length you need. You know what force per unit length you need. Now you need to know what force per unit length it can give you. And here's the only one of which I'm certain, and the other I'm so-so. In this formula, everything is the same, except you see that this depends on sine of phi, of theta. Now, the forces are changing angle all over the place. If it's perpendicular, I'm getting up to a 50% extra credit. What people do in the US at least, and I need to find out more about Canada, they say, forget the extra credit. Forget the extra credit. So we are not going, this thing in parentheses is going to go away. Credit for the for being more perpendicular. It would be very difficult to analyze. Very difficult. The other thing that I think should be in, is not in the way the American literature does it. Here you have a knockdown. This is not going to fail all at the same time, right? It's not going to fail all at the same time. If we were to talk conservative, we would say this is longitudinal, this is transverse, and this would be a point. If this is 0, right, this goes away, and when this is 90, this becomes a 1. So it can be as small as 0.85, but they don't do that in the literature that we have from the labs. So they don't do this, and they don't do this. And voila, you can do the same process as before, because you knew the force per unit you needed, and now you know everything except the size of your throat. And you calculate the throat straight from there. It's pretty amazing. Now you can calculate crazy stuff with this. Formulas are calculated, right? So when you see things like this, it might look intimidating. But think how awesome. When I was in engineering school, we need to derive this. And it's in a table. Awesome. Like, you just use it. You just look what you think is the one that most represents what you have. Right here you have like one line. Here you have two parallel lines. Here you have an angle. Here you have a right angle. Here you have. I need to find out and figure this out. Oh, like things we can. So this is when one weld and two and two, 2 and 1. All right. I think this is a good time to stop before Mitch takes over and does it properly step by step. Do you guys have any question right now? Yeah. Oh, I lied. I'm sorry. The midterms are ready. They are great. The average is 80%. I left them at home. I'm so sorry. I meant to break them. I'm super sorry. I'll bring them tomorrow, and I'll give them to the front desk in Kemi Marcy. So you can ask Marcy for your exams. And if not, I'll bring them on Tuesday. I'm super sorry. I promised them for today. They are ready for today, but not ready for you because I left them at home. Super sorry. Right? Right. Let's take a 10-minute break before